here's our thought puzzle. When at rest on the launch pad, the force of gravity on the space shuttle is quite huge. It's the weight, mg, of the shuttle. When in orbit, 200 kilometers above the Earth's surface, the force of gravity on the shuttle is A, nearly as much, B, about half as much, C, almost zero because of microgravity, or D, exactly zero. And to make the math easy, let's ignore the change in mass that the fuel burning would create. Let's just pretend it has a constant mass, because I don't want to have to deal with that. What do you think? What would the force of gravity up there be? Yeah.
Nearly zero.
I don't know. Let's see if we can figure it out. On the Earth, Matt, when I said get the obvious one last year, what did you always write in a free body diagram? mg. What did the little g stand for? We called that gravitational field strength. And if you have your formula sheet out by now, which all of you do, we have an equation for gravitational field strength, and it comes from Physics 11. So, Matt, if Fg equals mg, the equation that I gave you for gravitational field strength on your formula sheet in this unit is that. See it? And I'm probably dropping a pretty big hint here about your upcoming test, so you might want to pay attention. Except because we're going cosmic, this Fg, I have to use Newton's universal gravitation equation. Matt, from your formula sheet, what's the universal gravitation equation, the more complicated Fg? You're in the gravitation section still.
Fg equals
Big G, big M, little m over r squared, yes?
Yeah.
Okay. And what really happens is, can you see a little m is going to cancel? There's one on the top and there's one on the bottom. Okay? So this right here, and I did this on purpose, is the equation for universal gravitational field strength. If you crunch it while on the Earth, you will get 9.8. Let's crunch it for this space shuttle. What's big G as a number exactly? 6.67 times 10 to the negative 11. Let's get our calculators out. Let's try and do this without actually writing anything down. Let's just go crunch. So 6.67 times 10 to the negative 11. Big M would be mass of the Earth. 5.98 times 10 to the 24th divided by... they gave me 200 kilometers. Do I do physics with kilometers? So I'm just going to write 200 in brackets times 1,000. That 200 kilometers, is that the distance from the center of the Earth, or is that an altitude above the Earth? According, you can't see because I'm covering it up, according to this question. I think it says above the Earth. So I'm going to have to add the radius of the Earth to that to make it a true radius. You're typing along with us, yes? 6.38 times 10 to the 6th. And then don't forget there's a squared on the r in this particular equation. So close your bracket off and square it. You were supposed to be typing along with us because you were going to see the punchline and realize that the answer is not C. Ben, what'd you get on your calculator?
9.212.
What's little g? What's the gravitational field strength up there? Say it again.
9.212.
What's the correct answer? A, B, C, or D? It's almost as much gravity there than it is on the Earth. So then here's the question. Why are they all floating? Or on the International Space Station, why are they floating? Because there's gravity up there and almost the same as the Earth. No normal force? Why is there no normal force? They're in free fall. That's the key idea. So Matt, it's a common misconception. I'm kind of glad you made the mistake of, oh, well, there's no gravity because they're floating. No. There's absolutely gravity up there. And you can see when you crunch the numbers, it's almost the same size as on the Earth. It's just slightly less. But they're in free fall. So because they're in free fall, no normal force. Is that okay? Today, I'm not going to be teaching you anything new per se. You're not going to get any new equations. In fact, if you look at the gravitation section, you'll notice we're done. What I'm going to be teaching you today is some applications. I'm hoping to look at pretty much every possible approach or application. When do I use work? When do I say there's a change in height, change in speed, conservation of energy? When can I say gravity is what's pulling me in a circle? This lesson's going to take 2 classes, and then we're going to do one more lesson looking at black holes, because black holes are really cool. Oh, students like me, I can usually get away with a fair bit. I called this Orbital Mechanics. And what I really mean is, hey, different approaches to stuff in space. Here's our thought puzzle. It says this: a mass little m, let's make it a rocket, is moved from the surface of a planet to a distance big R from the planet's center. Which of the following is true about the work done? So here's a picture. We're moving from a distance little r, which would be the radius of the surface of the planet, out to a distance big R from the center of the planet. Which of those work equations is correct? Excuse me. You know what? Instead of trying to eliminate each one, why don't we just derive the work equation and then see which one matches that? My first thought is, don't write this down. Work equals force times distance. Why can't I use that one? So what about cosmic? In terms of physics, why can't I use this one? What was the restriction on using? This had to have a constant force. And unfortunately, gravity, as you move further and further away, does get weaker. So I think that gets rid of A. Yes? In fact, I think that also gets rid of B, because I think B is force times change in distance. I think they're trying to say, well, work is a change it. Maybe you're doing it that way. In fact, I have to use my yuckier but more flexible definition of work, which is what? Yes. Looking at this picture, I'm going to assume that the change in kinetic is 0, because it doesn't say the word orbit. It just says moved. What's change in anything? So this is going to be negative big G, big M, little m over, instead of R final, I think R final is big R from the picture, minus negative big G, big M, little m over, and little r is R initial. What did you say, Brendan? What's the correct answer? Oh, I thought I heard you say the correct answer. Sorry. Okay. What is the correct answer? D. Okay. There's a minus minus, which would become a plus. By the way, if you wanted to write this slightly differently, you could factor out the big G, factor out the big M, factor out the little m, and then you'd have negative 1 over big R minus 1 over R. I've seen some textbooks that write it that way because that's maybe a little easier to type in one fell swoop if you want to. I'm not a big fan of writing it this way to get big R or little r by itself if they asked you to find those. This is a yucky equation to work with because not only are they on the bottom, you've got multiple fractions. I'm not a big fan. So you might see it that way, but nah. Let's talk about escape velocity. By the way, it should be escape speed because it is a scalar, but in the industry they call it escape velocity, and so Chad, reluctantly, I'll call it escape velocity, but I'm telling you we're going to solve it using a scalar method because it is a scalar. So escape velocity, speed, speed. What is escape velocity? Escape velocity imagines that you fire your rockets to hit full speed and then you shut your engine off and coast the rest of the way. If we ignore air resistance, how fast do you need to hit before you can shut your engines off, coast, and get away from the planet? Escape the planet's gravitational field. In fact, we want to do even more specific than that. So if my desk is the planet and this tennis ball is the rocket, what we want to do is hit full speed right away, boom, coast. As we coast, we'll be slowing down because gravity will be slowing us down. But we want to reach the edge of the universe all the way out to infinity, because that's what it really means to escape a planet's gravity. But we want to do it so perfectly, slowing down, slowing down, slowing down, that right when we get to infinity, Ryan, we also come to a stop. We don't want to waste any fuel. We want perfection. So what I wrote here is to escape from a planet's gravity means, in theory, to travel an infinite distance from the planet. In reality, it means you go far enough away from the planet that the pull of gravity is so small that, we ignore it. To barely escape, which is what we're going to do, means to escape from the planet with no kinetic energy left at the end. So you're going to end up at rest and at an infinite distance. And we can solve for escape velocity speed using conservation of energy, because there is a change in height and a change in speed and a yucky curvy graph, and it doesn't say how much work. So let's write KE initial plus PE initial equals KE final plus PE final. Kinetic final, we want to be 0 because we want VF to be 0. We want to be slowing down, slowing down, slowing down, slowing down, and exactly come to a stop once we've escaped the planet's gravity. But we also want to end up out at infinity. How much potential energy will I have out at infinity? Well, if I escape the Earth or the planet's gravity, and I shut my engines off, will I fall? So how much potential energy must I have if I won't fall? And so this is also going to be 0. That's because it's relative to 0 at infinity. And so you have this strange situation, Ben, where the right-hand side, both zeros. Okay, so we get this. KE initial plus PE initial equals 0. Okay. Let's plug in our equations. So kinetic energy is going to be a half mv initial squared plus, we are going cosmic, so not mgh, but negative big G, big M, little m, all over r initial equals 0. And I want to get the v by itself. I think the first thing that I would do is plus this negative term over to that side and replace the 0 with that. I'll get a half m v initial squared equals positive big G, big M, little m over r initial. Oh, cool. Will the escape velocity for a big Saturn V rocket or the space shuttle be the same as the escape velocity for a smaller NASA probe? Why? Well, that's kind of nice. And now, Nick, I just want to get the v by itself. How would I move that 1/2 over? Times by? And then how to get rid of a squared? Thank you. I get this. 2 big G, big M over R square root, which is really a pretty answer. By the way, look up for 1 second. That is orbital speed. That's escape velocity. Orbital speed, escape velocity, speed. Orbital speed, escape velocity. And so for what it's worth, it turns out once you're in orbit, if you want to leave the planet, you need to go root 2 times faster, 1.414 times faster, and that'll get you off out of the planet's gravity well and out into wide open space. And so, well, I'd like to know escape velocity for the Earth and for the Moon. Let's do A, the Earth right here. Let's do B, the Moon right here. So escape speed is going to be the square root of 2 big G. Mass of the Earth is 5.98 times 10 to the 24th. Radius of the Earth is 6.38 times 10 to the 6th. What do you get? Square root. This one I've inadvertently memorized because it's almost 11111. It's almost 11,111. I think one of the digits is not a 1, but I just memorized it because it's almost 5 ones. Is it? I think it's 11,181 or something like that. Is that right? 11,200, let's say. Worked okay? And we do that. Anytime we've sent probes out to the edges of the solar system, they've had to hit escape velocity. The Saturn V rockets had to hit escape velocity. We got the astronauts partway to the moon, and then they coasted the rest of the way until the moon's gravity grabbed them and started speeding them up. So we can do this. Do you expect the escape velocity for the moon to be bigger or smaller than the Earth? Smaller. Have I showed you the we should be building moon bases video yet? Okay, we may get to that today. I don't know yet. So let's find escape velocity for the moon. It's going to be 2 big G. Mass of the moon, it's on your sheet. I think it starts with a 7, but I can't remember anything else. Times 10 to the what? 22. Divided by, and radius of the moon on your sheet. Starts with a 1. What's the moon's escape speed velocity? Think you get something in the 2000s? I think. I could be wrong. Oscar, what'd you get? 2,370? If I go 11,200 divided by 2,370, almost 5 times faster to leave the Earth. And remember, kinetic energy has a squared in it, so it takes roughly 25 times more fuel to launch from the Earth than it does to launch from the moon. So from a purely economic standpoint, I hope your generation is the generation that has moon bases. We can make fuel on the moon. There is water on the moon, and hey, that's hydrogen and oxygen, which is some of the best rocket fuel out there. So I hope. That's escape velocity. I am going to ask you to do an escape velocity question on your test. You can, some kids choose to just memorize this equation. You can add it to your blue sheet, not to your yellow sheet. Or you can do the derivation, and the derivation is it's conservation of energy, but the final equals 0 and get the V by itself. It is possible to reach infinity, Nick, and still be moving. That would look like this. KE final plus PE final equals KE final. Plus 0 because you're out at infinity. But that would just mean, oh, you got some extra energy left over. It must be kinetic. Can't be potential. Oh, initial and initial on the left-hand side. Thank you. By the way, the corollary of this, any asteroids, any meteorite, any space debris that comes from out of our solar system must hit the Earth at least 11,200 meters per second, because it's going to gain all of that energy back in the form of kinetic. Plus, it would have had its own kinetic energy because it's coming from outside of the solar system, so it's already got some of its own speed. This is why asteroid impacts are not a good thing. I didn't, that's not in your notes. I thought of that actually after I typed these notes up. I thought, oh, that's kind of cool. That's just hashtag nerd trivia, not on your test, but kind of cool. Now you can turn the page. Let's talk about black holes. Those are pretty cool. What is a black hole? Yeah. That doesn't necessarily make it a black hole. What property does it possess? Why do we call it a black hole? Doesn't suck in light. Pardon me? Doesn't have an infinite mass. In fact, often they have fairly small masses. So what a black hole is, remember at the beginning we calculated little g? Okay? It's a stellar object that has a gravitational field so big that the escape velocity is bigger than light. Okay? So if you calculate the escape velocity, you get an answer bigger than light. Can anything go faster than light? So can anything escape it? Including light. And that's why they're called black holes. It's not that they suck in light, it's that once light enters, once anything enters, it ain't coming out. Okay? How do you do that? Start with it. You're right, that's how a black hole is created. You start with a big star, lots of mass, and remember, well, A. A spaceship is 8.5 times 10 to the 9th meters from the center of a black hole. The black hole has a mass of 50 times that of the sun. Find the gravitational field strength. Cool. Nice. Chad, how am I going to, what's this question asked me to find? What's my equation for gravitational field strength? Are we in orbit? So, and by the way, Chad, you made a mistake, but I'm glad you did. So Chad, first of all, said this. Chad, do you see the word orbit anywhere in this question? Can't say that. How do I find gravitational field strength? Look at your formula sheet. Yeah, good call. Chad said this, big G, big M, little m over r squared. It's funny, every class has made this mistake. And I apologize for picking on you, but I'm glad you made this mistake. What is that? What would I write on the left-hand side here? Capital F, lowercase g. Yes? What does that letter F stand for? What word is that? What does this letter stand for? This is the problem. I am going to ask you to find a gravitational field, and many of you are going to find the gravitational force. And the difficulty is I have to give you 0. It's like I asked you to find the acceleration, and you found the distance. Well, I'm glad you found the distance correctly. Good for you. Not what I asked for, just because they both begin with F. Oh, and it's also tricky because this is the force of gravity, and this is the gravitational field strength. So what you're going to need to memorize or drill into your brain is gravitational field strength is little g. There is a formula for little g on your formula sheet, Chad. Can you read it to me? Big M or little m? Fg, we're cosmic. Now can you read to me the Fg equation that you read a few seconds ago? Are you having a little deja vu? It's that thing that we did for the space shuttle question at the beginning of class. Okay, so Ethan, as r gets smaller, as the star collapses on itself, what would happen to this answer? And there comes a point when the gravitational field strength is so big that light can't escape. And yeah, we'll calculate that a bit later because why not? Okay. For now, we want to calculate the gravitational field strength that this spaceship is at 8.5 times 10 to the 9th meters from the center of the black hole. Okay. It's going to be big G, 50 times the mass of the sun. It's on your sheet. What's the mass of the sun? Starts with a 1, I think. 1.98 times 10 to the all over. Chad, that 8.5 times 10 to the 9th meters, is that an altitude or is that measured from the center? So I don't need to add any, which is good because they didn't give me the radius of this star. Okay, 8.5 times 10 to the 9th. Don't forget the squared. I'm expecting an answer bigger than 9.8 because black hole. What do you get? Yep. Brennan, what'd you get? Yep. What'd you get? 91.4? And you didn't hear Adam. Adam said, "Don't leave my calculator made a dumb mistake." The reason I keep yelling at all of you to practice the typing is it drives me crazy. This is the test where I see by far, and I don't use this word very often, the stupidest calculator mistakes. And it's because the kids were too lazy to practice during class. Make your dumb mistakes now. You want to be an expert on your calculator by the time we get to the test, because having all the right numbers and wrong answer, that's just throwing away silly marks. Chad, what are the units? Ready? You told me this. Yes? What do I measure F in? What do I measure M in? So the units must be. However, isn't force divided by mass also acceleration? You could have written meters per second squared here, because if you muck around with the units, you'll find newtons per kilogram does simplify to meters per second squared. Although I would also say anytime I'm talking about a gravitational field strength, I'll almost always use those units, because that contains the equation to solve gravitational field strength hidden inside of it. Take the Newton force of gravity and divide it by the mass in kilograms. Is that big? How many G's is that? In your head, divide by 10, roughly. It's about 9 Gs. Yes? Are the astronauts in trouble? Let's suppose we put them there for a month. Are they going to survive? It depends. Let's suppose we put them in an orbit for a month. Who remembers the space shuttle question we did at the beginning of class? What was G on the space shuttle? Do you remember what we calculated it to be? 9.2. Do the space shuttle astronauts feel the 9.2? Why not? Because they are in free fall. Would these astronauts feel the 91.4 if they were in orbit? No. Why not? Because they are in. So actually, as long as they're in orbit, they're okay. The tricky part would be inserting into the orbit, because you would feel it then, and getting out. So this would have to be done maybe with Star Trek transporter technology or something. You beam them right into that location, and they'd be okay if you put them in a stable orbit right away. Okay? But if they were in a stable orbit, you wouldn't notice this. Okay. Because the same way the astronauts don't notice the 9.2. I don't know. I'm in free fall. Coming in and getting out would be problematic, though. In fact, let's try and get out. B says, how fast would the spaceship need to travel in order to escape from the black hole's gravity well? Don't look back. Just for practice, because this is what you would have to do on a test, let's derive this from scratch. Escape, I think it's asking me to find escape velocity, speed. How did we find escape velocity? Speed. What did we use first? Conservation of energy. So I would say, okay, KE initial plus PE initial equals KE final plus PE final. Oh, wait. We said really 0 and 0. And it's a little weird because you're saying, I'm starting with a whole bunch of energy and ending up with 0. That's because this one is negative. This one is positive. And really we're saying how much kinetic energy do you need to cancel out this negative. In fact, we're going to get this, I think, a half m v initial squared minus big G big M little m over R initial equals 0. We're going to get a half m v initial squared equals positive big G big M little m over R initial. Since there's only one R, I've dropped the initial and just started writing R. Little m cancels. Yay! Can you see it from here? Times by 2, and then square root. So the escape velocity, speed, is going to be the square root of 2 big G big M over R. Let's plug in numbers. It's going to be larger than 11,000 because black hole, because the gravitational field is so much stronger. Of course, we're going to need to do more. It's going to be substantially larger than 11,000. I think you get an answer that starts with a 1. And I think it's in the millions, isn't it? Yeah. Haley, what'd you get? 1. Give it to me in scientific notation. Give it to me in 1 point what? 1 point what? Is it 2.5 or 2.6? You round up. 1.25 times 10 to the 6th meters per second. With our current technology, probably not doable, but now let's go sci-fi. Hey, it's the Starship Enterprise. Is that faster than light? What's the speed of light? Who remembers? Did I give that to you on your formula sheet in the constant section, maybe? Can you check?
Yes.
Okay. Is that faster than light? No. So it is feasible to escape if you have Star Trek technology. But, let's see. The event horizon, that's the fancy name for where your escape velocity becomes faster than light. This is asking how far away from the black hole is the event horizon. We're going to start out with the escape velocity equation. We're going to get the r by itself because it's asking how far away. But we're also going to do this. We're going to let the escape velocity be the speed of light. Except we have a symbol for the speed of light, do we not? See what? Or are you saying yes? Okay. So I want to get the r by itself. What's the r inside of? What's the r inside of? So square both sides. We'll get v squared equals 2 big G big M over r. Where is the r right now? On the... Well, I didn't, technically not a swappy dance, we're cross multiplying, but you're saying I can multiply the r to the top and move the v squared to the bottom? Yeah. R is going to be 2 big G big M over v squared, where v is going to be 3 times 10 to the 8th, right from your formula sheet. It's going to be 2 big G 50 times 1.98 times 10. And this is how we can calculate, going back to your definition of a black hole, Ethan, which wasn't quite right, but pretty close, how small this star would have to have collapsed to before it would be classified as a black hole. I have no idea what the answer here is. I'm kind of curious myself. Oh, works out even. You get 146,740 even. Okay. Or if it's smaller than, so first of all, as soon as the star collapses past that, its gravitational field would now be enough at that location that light can't escape. So that's where you would, if you were standing there, if you were Superman and could somehow have superhuman powers, that's where you would see, oh, no more light coming out. It's far more complicated than that, because even near the event horizon, there's some weird space-time stuff going on. But certainly any smaller than that, or if you went closer than that, nothing's coming out. You're not coming out again. So I'll go scientific notation 1.47. 47 or 46, Mr. Duke? 46. 7 times 10 to the 5th meter. 5th? Yeah, meters. Turn the page. We're going to pick up with example 4 next class. It's the longest question of the year. What's it asking me to find? How much what? To put it into a stable what? So I'm going to go change in potential plus change in kinetic. But because we're in a stable orbit, change in kinetic is not going to cancel, unlike just lifting it. We did this question last class, except there I gave you the speed, the orbital speed. Did I give you, Nick, the orbital speed in this question? You're going to have to go gravity is what's pulling me in a circle and actually calculate the speed. It's about 11 steps. It's doable. I'm not going to give you one that long on your test. I'm doing it. They used to do this one on the provincial, but it's just so much writing. I'll tell you exactly on your test what parts of this I'll ask. I'll ask it in chunks. Put your pencils down, look up.